Okay, so we finally had got one more rule to add to our language of or logic, and that's the while rule. And the while rule allows us to add looping to the language. So what is the while rule? The while rule states that if you have some Hall triple of the form precondition P and B, code S, postcondition P, so this is the same P on both sides, and we call P an invariant because the truth value of P is left unchanged by the code S. P is invariant of the code S, if you like. So if this condition holds, then I can say, assuming if P holds, while B is true, keep doing S forever until B is falsified, and then afterwards P is still true because P is left unchanged by S, but B is now false, because the only way we could break out of the loop, the only way this while loop would terminate is if B was false. So now I've got this new rule. I'd like to finally prove this statement we talked about so long ago. If x is greater than or equal to 0, while x is not 0, decrement x by 1 until x is equal to 0. Okay? So let's use our new while rule to prove this. So the first thing we do is, as usual, we write our goal down the bottom. X greater than or equal to 0. While x is not 0, decrement, and then postcondition x is equal to 0. Okay, so the idea is I want to use the while rule backwards. And the problem is this statement here isn't quite of this form, right? If I sort of like annotate each part, so this is P, this is B, this is my code S. This thing here doesn't look like P and not B. So what I can do is I can try rewriting the postcondition so it looks like P and not B, and see if I can jump from my postcondition down to here using postcondition weakening. So let's just try that and see if it works. So x greater than or equal to 0, that's my P. While x is not 0, that's my B. Do the code S, decrement x by 1. And now I'm just going to write in P and not B. So P, x is greater than or equal to 0, and not B, x is equal to 0. Alright, so our postcondition is now x is equal to 0 and x is greater than or equal to 0, which looks logically equivalent to this one here, right? Because the x is greater than or equal to 0 is like redundant information. Cool, so if I can prove this, then I can prove this by postcondition equivalence. And this statement is now the right form, right? Because I've got P, B, S, P, and not B. If I'm being particularly pedantic, I really should have written that as the negation of x not equal to 0. And then negation of x not equal to 0. Because to be the form to use this formula, it has to be precisely of the form B and not B. So B and not B, precisely of that form, right? You don't want to simplify stuff until you do the logic step. So now to prove this line here, I can use the while rule backwards. So I'm going to do that. So we have P and B, the code S, and then P, which is x greater than or equal to 0. Okay? Before I go any further, I should check, is this thing provable? Like, does this thing make sense? What is this saying? This is saying that if x is greater than or equal to 0, and x is not 0, so what's that say? It says x is strictly greater than 0, and I subtract 1 from it, then x is greater than or equal to 0. I mean, yeah, that seems true. From this condition here, x is bigger than or equal to 1, and if I subtract 1, it's going to be bigger than or equal to 0. So this looks like a true statement I should be able to prove. So let's prove it. I guess I'll do assignment backwards from the right-hand side like I usually do. So x assigned to be x take 1, x greater than or equal to 0. And I'll do assignment backwards, so replace the x with x minus 1s. Okay, so this statement here says x minus 1 is greater than or equal to 0. So I'll just annotate my margin here. If x minus 1 is greater than or equal to 0, that's if and only if x is greater than or equal to 1, which is if and only if x is strictly greater than 0, which is if and only if x is greater than or equal to 0, and x is not equal to 0. Cool, that checks out. So then I can write x minus 1 is greater than or equal to 0 if and only if x strictly greater than 0 and x not equal to 0. So these two preconditions are equivalent. So it looks like my proof is done, right? All I just got to do is put in the rules and annotate everything. 3, 4, 5, 6. So this was assignment. This was logic. This was something, precondition equivalence. Precon equivalence, lines 1, lines 2. This was the while rule by 3. This was logic. And this was postcondition equivalence by 4 and 5. So once you've got rid of the whiles by using the while rule backwards, you can just attack this problem with all the whole logic you've learned up to this point. So the only scary bit, the only new bit is getting rid of the while rule. Once I've done that, you can just use all the stuff from last week to solve this problem here. Okay? So that's how you can formally prove this is a valid Hall triple using the while rule.